I'll give you that back.
Thank you.
All right. Good afternoon.
Hello.
Come on, you can do better than that. Good afternoon. Awesome. I'm glad to be here. Thank you, Julie, for the warm introduction, and glad to see so many people here. Please, for those of you who are on the webcast, please speak up if you can't hear me for some reason, because I do tend to walk around just a little bit at the front of the stage, but I'll try to stay close enough to the laptop that you can hear me on the recording too. So, we're going to start with the encryption session. And this is a combination of my standard encryption session with a lot of added focus on always encrypted, because that is a relatively new feature that a lot of people aren't familiar with. So it'll be a little bit longer than my normal type of session, but I'll try to. What's the time? What time do you normally take break, Julie? About 2:30.
Usually an hour and a half presentations, and it goes around 4.
Okay.
Whatever
So
you need.
I'll try to stick as close to 2:30 as I can. So 2:30, 2:45, something like that.
We'll just take a break and then start the second. Whatever.
Awesome.
We're flexible.
Okay. So as Julie said, my name is Dick. I run a consulting firm out of Cedar Rapids and Iowa City area called Kingfisher Technologies, and I'm a data architect. My focus is on the database administration side of things, more in the SQL Server engine than on the BI type of space, but I kind of do a little bit of everything. Everything from traditional performance tuning to ETL, but one of my real focuses and one of my passions, especially in the last couple of years, is security. Because it's a topic that we really don't talk enough about, especially in the database community. And the reason that I feel like it's such an important topic is that we have all of these attacks going on, and the one thing they all have in common is that they want our data. And we have all of these. We'll talk more about this later on, probably, I think, in this deck anyway. But a lot of times when we talk about security, we're focused totally on the perimeter. We're focused on the network and the gates in, but we don't actually secure things that are actually valuable, at least not well enough. And so that's the reason for talking more and more about this topic, is to help people understand what they can do to proactively prevent a data breach, even if your network is compromised. I'm very, very passionate about the community. I've been involved in it for about 11 years now, and I absolutely love it. This will be my 10th past summit up in October, and I'm very, very pleased and privileged to be able to do that. And I am, as Julie mentioned, I am a Microsoft MVP. So I'm very, very fortunate, and I love to be able to share and give back to the community what I've learned, because the community has given me the opportunities that allowed me to be what I am today. So, as I mentioned, I will be at Past Summit. I'm giving 2 presentations there this year. One is on kind of the next chapter of encryption. This is going to talk about how to set up encryption and how to use the various types of encryption that we have available to us in the SQL Server world. The next step is, how do you maintain that after you set it up? Because a lot of people treat it as a one-and-done operation. Hey, great, I secured my data. And then they never look at it again. But really, in order to be able to maintain that and keep that as secure as possible, there are some things that you need to do, and we'll talk about that in one of my sessions at Summit. The other is focusing on auditing and monitoring. And what can you do on a daily basis, or even a weekly or monthly basis, that those regular checks to make sure that you're staying on top of your SQL Server environment and the security in that. And that's going to be the topic of my other talk at Summit. So hopefully I'll see some of you there. And if you do make it there, please stop me and say hi. Okay, so for this first talk, we're going to talk in depth about encryption. And this is a very broad talk. If there's any questions, anything you want me to go deeper on, just let me know. But we're going to start talking about just a little bit about why we actually want to make sure we're using encryption in our databases. Followed by the three primary types of encryption: in column, at rest, and in transit. And then we'll talk more in depth about always encrypted, because that's a topic that a lot of people aren't as familiar with. And then what do you need to do to protect your keys? Because that is really a crucial part of any encryption scheme. Okay, so why should we do this? And some of these initials, I've been talking about encryption for a few years now, so some of these slides are a little bit dated. There's even more impressive is the only word that comes to mind, but it's kind of depressing statistics out there now. But in 2014, for the first time, we crossed 1 billion records lost in 1 year alone. That growth is continuing exponentially. So far this year, if I remember my statistic right that I pulled for another class, I believe we've lost somewhere in the neighborhood of 5 billion records already in 2017, and that was a couple of months ago. The growth in the amount of data breached worldwide is just incredible, and it doesn't show any signs of slowing down anytime soon. Anthem was one of the first big public data breaches. That was back only in 2014. We'd had some other ones before that, but this was one of the first big ones that really started to get people's attention that, hey, we've got a serious problem. They're really going aggressively after our data. And the sad thing about the Anthem breach is that it was completely preventable. From what has been made public, it appears that it was completely preventable. They had Anthem the social security numbers and other personally identifiable information in their databases completely unencrypted. They didn't think anybody could get through. They didn't think it was necessary. Nobody's going to come after us. Companies large and small are finding out that's no longer the case. These are just some of the big breaches in the last 12 months. Yahoo had 2 significant breaches actually that occurred back in, I believe it was in 2014, but they weren't publicized until last year. One of them lost 1 billion records, the other one lost 500 million records. The U.S. government was hit very hard last year, everything from the suspected election hacks to Department of Defense, Department of Homeland Security, a number of other prominent breaches. Healthcare, I already mentioned that one. That's becoming an increasingly large target because of the high personal information that they can gather from that, and the relatively low security a lot of healthcare companies had traditionally placed on that type of information. Small businesses became a massive target last year. Again, hackers finally realized that there's this wealth of information out there, and most of it is unprotected because small businesses don't have the manpower or the knowledge to be able to do that. And then finally, the big one that broke this last week, Equifax. In the Equifax hack, we're still finding out a lot of details about it, but the early indications are that the hackers exploited a vulnerability in the Apache Struts web application framework, which allowed the hackers to directly access web-based APIs and literally mine any public-facing data they wanted to. That's scary. They say that there's no indications at this point that they accessed any private credit data, but that's okay because it's your social security number, your birth date, your driver's license, your address, your phone number, and your name that were breached. That's all. So this is becoming a larger and larger and larger problem, and we need to be paying attention to it. Encryption provides assurances to our stakeholders, and this includes not only customers, but also employees, management, investors, directors, and so on. It satisfies regulatory requirements. How many of you, well, first of all, how many of you are DBAs in the room? About half. How many are developers? Okay. How many of you work for a company that's covered by something like HIPAA? Few. How many are covered by, or a public company covered by SOX? Couple. How many of you don't think you're covered by any sort of regulations? Okay, that's good. Because most, even if you don't have government regulations, you may have contractual obligations to your business partners. Even, especially if you do business with a healthcare company. You may be covered by a BAA or a business associate agreement that requires you to follow the HIPAA regulations, at least to some degree. Encryption also provides a fail-safe for when every method fails. An example I like to use is the password management company LastPass. How many of you know that they have been breached twice? A couple of people. The reason this did not make major headlines, because no data was lost. The hackers downloaded the database, but because it was very strongly encrypted, there was nothing for the hackers to really get. They would have to expend way too many computing cycles in order to get at this data for it to be worthwhile for them to even try. And this is the reason that we use encryption. Even if they do download something, encryption renders it useless to them, as long as you're using a strong encryption. So this is a very, very simplistic diagram of a common network right now. You've got the internet, the cloud out there. You've got in the middle, or down here at the bottom, you've got your corporate network. Very, very simplistic again, as I said, but it is a common network configuration with a simple backbone. In the middle, on the pipe coming in, you have a router, a firewall, intrusion detection, and maybe intrusion prevention systems. Probably a whole laundry list of different types of appliances in order to be able to the traffic coming in to try and keep everybody out. Internally on the individual desktops, generally not on servers because they're processor intensive, but on the desktops you've probably got some sort of endpoint protection. Antivirus only installed on everything. On desktops, you might have something that has a software firewall, or you might have some sort of other malware prevention to try and plug the holes there. But generally, if a hacker can breach any individual point inside your network, in many corporations, they have free range over at least a portion of the network, if not the entire thing. That's just a standard configuration. That's the way we've always done it. The problem is that if they can get in here and they can start moving around the network, they can eventually find your database server. And that's when we need something else to stop them. This isn't the silver bullet, though. I don't give anybody the impression that it is. Encryption protects against mass data theft. It prevents them from downloading the database file, and prevents them from downloading a database backup. This keeps the company off the front page, but it may not prevent them from downloading individual records. It may not prevent an insider from downloading a spreadsheet of all of your customer information and sending that out somewhere. It does not prevent against a hacker gaining credentials that give them access to the database and downloading individual records. All of these are outside of the realm of things that encryption is designed to prevent, at least the state of encryption as we have it today. And so you still do need to use defense in depth and use this in combination with other technologies. But it can be a really powerful part of it if used properly. Your goal is to not be this guy. You will have heard the story about the two men in the bear. One guy looks to the other guy and says, I'm sorry, I'm terrible at telling jokes. One guy looks to the other guy and says, "We got to run away from this bear." The other guy says, "No, I just have to stay in front of you." You don't want to be the guy that's in last place if you're running from a bear, because guess who the bear is going to catch first. Same is true with encryption. You want to make your company a harder target than somebody else because there are so many possible targets in the world right now that the hacker will probably move on to someone else. And that's kind of a cynical point of view, but it's absolutely true. You want to make yourself a harder target. That's why you put all those deterrents in front on your network to try and get them to just go away in the first place. But the encryption also makes it so that they have to spend a lot of time, a lot of energy to try and get out your data, which makes you a harder target, which makes them more likely to move on to somebody else. Again, not bulletproof, but it can definitely help. So this sounds kind of difficult, and it really is. It can be very difficult. It can be time-consuming. But it's not necessarily as hard as you think, and it's not as hard as it used to be. We've got a lot of tools that we can use now to help with encryption. There's built-in support in SQL Server. There's built-in support in .NET. There's built-in support in many of the languages that we use. Once you get it set up, the day-to-day management is minimal. There are some things you need to do to protect your keys, as I talked about it in my summit session for this year. There are some things that you need to do long-term, but day-to-day, there's very little management required of this sort of solution. Okay. Anybody not convinced yet? Need I go on? Okay. So in-column encryption. Let's start with that. In-column encryption is probably one of the most common things that you've probably already run into at some point, okay? Especially developers. DBAs, probably. Developers, definitely. And we've got two main types. One is called a hash. The other one is true encryption. The difference is that one is reversible and one is not. A hash is not reversible. With a hash, you send a piece of text. It gets combined with some sort of a passphrase, run through a formula, which scrambles the bits, but you can't reverse it. It's mathematically impossible to reverse it using a hash function of any sort. And so this makes a good method of encrypting things that you won't need to look up again, such as a password. That's probably the most common for a hash. Also use a hash. If you've ever downloaded open source software, most of them have an MD5 hash or an SHA-1 hash now. And what those are to verify the contents of the file matches what was originally put out there. Because every different combination of bits produces a different, when it's run through the hash function, will produce a different output. And each and every time that the same pattern of bits is run through that same hash function using the same passphrase, it will return the same output. It's utterly predictable. And that's a great thing for things like passwords that you need to be able to look, or to be able to somehow determine, because now you don't have to decrypt that password. You just have to then hash what the user typed in as the password and run it through the hash function in the same manner. Because no matter how many times you run it through it, it's going to produce the same output given the same inputs. Because it doesn't have to worry about the mathematical tedium of being able to reverse the encryption, a hashing is very fast. It's very fast. However, the one-way nature also makes it impractical for a lot of our uses. So the uses are limited to things like a password, like a file hash. Okay, so let's see how this works. Pull up the right VM here. And for the most part, I do have the fonts larger so that you'll be able to read them in the back. But if you can't, just let me know, and I'll either bump up the font size or use Zoom. Okay. Just to make sure, because I can't remember clear the demo or not. You will all of these demos are already out on my website at laytondick.com, so feel free to go out and help yourself to that. They're under the tab. In the near future, I plan to get that into GitHub, but I haven't had a chance to set that up yet. All right. And for most of them, I do include some sort of a reset script that will get rid of the last time you ran the demo, as well as create the objects necessary for the demo. So for hashing, we'll use this little encryption demo database. And then we are going to create this procedure, which will allow us to create users. This function here, I should highlight this on the screen so the people on the webcast can see what I'm talking about. The hash bytes function is what handles the magic of doing hashing in SQL Server. It's a very simple function. You pass in two things. You pass in the function you want to use. At this point in time, always use SHA-2 512. There's several different hashing algorithms available in SQL Server. You want to always use the strongest one you possibly can. And so there may be limitations, like you may be working with something that only allows 256-bit keys. That's fine. You still use the strongest one you can. Under no circumstances should you ever use RC4. That was actually taken out of SQL 2016 because a few years ago it was cracked. And every possible combination is known. We'll talk a little bit more about that, about how that's possible in just a moment. But you want, if at all possible, you need to use the SHA-2 algorithm, a 512-bit key length. If at some point in time SQL Server makes something larger available, use it. It's just good. And then you pass in the password that you want to use. It's as simple as that. So we'll go ahead and we will run that function, or create the function. And now we'll run that function. Yes. Yeah.
Password for the hash.
I'm sorry? The key for the hash. I'm not.
Maybe I'm not.
Okay. Oh, the passphrase? Yeah. Sorry, I think I misspoke earlier. You pass in the same input into the hash function, and it produces the same output. There's not a passphrase involved in a hash. So we'll go ahead and create the pointy-haired boss here. And then you can see that it produced, down here on the bottom, our username of boss, password of password, and then the password hash is just what appears to be random numbers and letters. There's really no pattern to anything that we're going to see today once the value is encrypted. Okay, that's what you kind of expect. Now let's create a few more users and look at the users table again. And here you can see that the CEO, if you guys know Dilbert, you know the CEO isn't much brighter than the pointy-haired boss. He also chose the password, and he came back with the exact same string of numbers and letters. Everybody else chose a different password, you get a different string. Okay, that makes sense. That was what we talked about earlier. Same input, same output. However, that predictability is also an Achilles heel for hashing. And this goes for any hashing algorithm that's out there. No matter what, that predictability is its Achilles heel. That allows a hacker to create what's called a rainbow table. A rainbow table is the result when a hacker just starts creating all of the known possible values of the hash function for a given input. And so if we were to create a rainbow table here on this hash function, we might start with just hashing things like B, C, and just go down and start putting together all the possible combinations. And once we got done with that, we start going to AA, AB, AC, AD, and just keep going and going and going and store all of these values. Guess what? Now they have no computation required in order to know what the output of your hash function is going to be. And these rainbow tables are actually stored or actually compiled by a community out there. And some of them are even freely downloadable. That RC4 recommends more because there are so many rainbow tables for RC4 that it covers all of the known possible values that are reasonable to use. So let's look. This is what the rainbow table might look like for just our very simplistic example. But now I know what the values of these are. I just have to compare this value to what's in my password table, and I know what the password is. Obviously, that's not a good situation. So what you can do is what's called salting the hash. And this is a very common practice, and this is a very simple example as well. But the idea behind any sort of salting, or there's other variants, salting is the most commonly known one. There's also peppering, there's spice, and all of these are various combinations of this general pattern. Well, anytime you salt the hash, you add something to the value that some sort of known value to the value that you actually want to protect. So in this case, I'm going to use the ID column. It's a very simplistic database, a very simplistic example. Don't use this in real life because it's too easy to guess. But the idea here is we're now instead of hashing the value password, now we might hash the value password 12345. Okay. It's still something that seeing as how we know what it is that we are trying to derive, we know what the pattern is, and so we will be able to reproduce it. But it makes it that much harder for a hacker to be able to reproduce this, and much less likely that the rainbow table is going to contain the actual hash. Okay, and you can use any values you want to in this. It doesn't have to be any sort of known column. It can be something in a different table. It can be some sort of other value that you can derive. You can put anything in there as long as you will be able to reproduce it later. So you wouldn't want to hash in, for example, a date and time, like the current system date and time, because later when you want to be able to compare against that hash, you won't be able to. But if it's something like the ID, their email address, the department, some sort of other combination of fields, some sort of GL code.
That would be unique to the user?
It can be anything. A lot of times you want to have it be at least somewhat unique. The question is whether it should be something unique to the user.
You want it system-wide.
Right, not generally. Generally, you want to have it something a little bit more unique to the user, so it's that much harder for the hacker to guess. Some of these other patterns, I mentioned that we've got pepper and spice, and I don't even know what other names they've come up with for them. They combine these in various ways. One recommendation that a lot of people have is instead of just hashing this once or salting it once, you salt the original value, hash it, salt it again, hash it again, salt it again, hash it again, and some people will do this 3, 5, 7, 11, 20 times. And as long as it's a reproducible pattern, you will get the same output. And the more complex you make that, the harder it is for it to guess. Okay. So let's just do a quick example here. We'll modify our procedure to add in the hash or to add in the salt. And now if Bob and the garbage man both type in password as their password, and we look at the values, now we can see that Bob and the garbage man both have unique values, and it would be that much harder to guess that the actual value here would be password. Okay. To retrieve it, you as I said, in order to retrieve, quote unquote, the value of a password or of a hashed password, you hash the new value and compare it, because you can't actually reverse that hashing method. So if we do that here with Dogbert, we'll get a correct value because I rule everything was his password. If we do that for Alice, we'll get incorrect because that was not her password. And you can do this with SQL Server logins as well. There is a function in SQL Server called pwd compare that will use the hashing function that SQL Server uses internally for SQL Server encrypted counts to actually compare a value that you pass in to a value that it's already stored in its password tables. And the value here is that if you have a list of, for example, a list of bad passwords, because there are lots of lists out there now of, here's the top 1,000 overused passwords. So password 1, 2, 3, password exclamation point. All of these passwords that we know we really shouldn't use, but we do anyway. You could create a table, and you could routinely go through and you need to compare against your SQL authenticated accounts to see if anybody has used one of the weak passwords on one of those accounts. And then you don't necessarily have to know what the password is, but then you can go back to those users and say, we really need to change the password on this because it's somewhere in this bad password list, this weak password list. And that's a good security measure. It's actually something that I demonstrate in one of my summit sessions as a recommended practice to do, like once a month, once a quarter, just on a regular basis, so you can weed those out and over time improve your security. Okay. Questions? Yeah.
Yeah. Why doesn't SQL Server solve its password value? Because we compare work to seem that other.
They don't publicize their algorithms for obvious reasons. I have to assume that they do solve them. They probably do. Most companies, especially those that have any sort of reputation for security, are using some sort of salting, something more complex than just a very simple hash. So I think they probably are in the background. But remember, the same input is the same output. pwd compare uses that same algorithm. And so it's not that their algorithm is weak. It's just that they are exposing a way for you to use it as well. Does that make sense?
Kind of.
They're
not using just a straight SHA-2512 or anything like that.
But wouldn't you have to know the individual user's salt or whatever in order to add to the password you pass in, to then compare it and know that it's matching? Because otherwise,
it depends on how they're doing the salt.
Because you're just passing in a password to see if it matches their passwords from the table, right? So they have to be appending something to it.
They're doing something, but as I said, they don't publicize their algorithms, so there's no way to tell what.
They would be storing that salt somewhere internally. The same way, like yes, if you were using some unique value for each user to salt your hash with, you would have to store that somewhere.
Yeah.
So you could repeat it later on.
And it's very possible that they're using something that's system-wide or something that's derived somehow. There's no way to know exactly what it is that they're doing. What I can tell you is that they do expose this and it does work. You can use that to see if there are any weak passwords in your system.
And also just to kind of throw out there, if you do use some piece of user information for your salt, like the username or last name or as part of it, you have to make sure you update that hash if they edit everything.
Well, you wouldn't be able to, because you wouldn't know the root of the password in order to update it.
So, yeah, right, if it's part of
You
your
just rehash.
But if
it's
you don't
part
have
of your
the,
salt, you would have to
unhash
have them
that.
re-input their password in order to change that so that you could rehash.
Right.
That's exactly right.
Yeah.
That's the reason that on a web form, if you go in or something like that, that's part of the reason they ask you for that for your password again. Is because if they're using that piece of information as part of the salt, besides just being a good security practice, if they're using that piece of information as part of the salt, now they have the opportunity to re-encrypt all of that. So, other questions? Those are some great questions. Okay. Come on.
Did Microsoft's approach to that significantly change from 2008 or 2012 to 2016?
The approach, as far as I know, has not. The algorithm has. That's one thing that they do tell us, is that the algorithm does change. I can't say every version, but they have said that it has changed on a regular basis. So. Okay, symmetric keys. Symmetric keys are a little bit more complex. They are, and because of that, they are slower. They're also a reversible type of encryption, meaning that you can get the original value back. In this case, unlike when I misspoke earlier, they do use a passphrase on symmetric keys. So you pass in the text, you pass in the passphrase to use as essentially the randomizer for this. It produces the encrypted string. Then you can take and you can apply that same passphrase, and you can get your text back out that you originally put in, or number, or whatever it is. This is not as fast as a hash, but it's a lot faster than any other method of encryption. And so we commonly use this for securing data. But you can probably guess that having that same passphrase used to both encrypt and decrypt is a weakness. And so it's generally not used as the only method of encryption when it is used. But because of its speed, we use it a lot. One advantage is that the way SQL Server implements this is that a symmetric key can be encrypted by multiple protections at the same time. And this allows us to do what's called key rotation. And that is a good security practice to get in the habit of. That's the reason that anyway, it's a very good security practice to get in the habit of. SQL Server also does not allow you to back up a symmetric key because it is so easily recreated. Using the same passphrase creates the same symmetric key. Okay. An asymmetric key is kind of like what you use anytime you go to an encrypted website, a secured website. It's what's called public-private key encryption, and SSL, which is what's used to do a secure website, is a very common example of a public-private key style encryption, or an asymmetric key. In this model, you have one key which encrypts the data, but cannot decrypt it. And then you have another key which can decrypt the data, but cannot encrypt it. And so internally to your company, you'll typically have both. You'll have the public key and the private key. But you can get, because the public key, which is the one that can encrypt only, because that cannot be used to decrypt the data, you can give that out to whoever you want to. And you won't have any problems with it. Because it's mathematically impossible, or as close as we can get, to figure out what the private key is just from the public key. Okay. This is more secure. Just logically speaking, it's more secure. However, that also makes it much slower. Much slower. than symmetric key encryption. So what we typically do is we will use the asymmetric key to encrypt a symmetric key. And this allows us to have the best of both worlds. We can protect the symmetric key and then use the symmetric and then decrypt that once and then use that symmetric key to actually do the encryption of the data. You lose a cycle or two on your CPU for that method, but it improves the security dramatically and improves the speed dramatically because now you can decrypt a lot of records at once. A certificate is a special type of an asymmetric key. And there's a few differences between a certificate and an asymmetric key. One is that a certificate is based, the format is based on a standard called X509. SQL Server implements the X509 v3 version of that standard. Another difference between a certificate and an asymmetric key is that a certificate will expire. Any SSL certificate you buy, any code sharing certificate you buy from a third party will have an expiration date associated with it. Generally, they're good for no more than 2 years. Before the certificate authority will no longer recognize that key. However, for the most part, it works exactly the same way as an asymmetric key. You have a public key that encrypts, a private key that decrypts. It is still a specific implementation of an asymmetric key. I mentioned that the certificate can be purchased from a third party. You can purchase one. It's called an authenticode or a code signing certificate. Because you can purchase that from a third party, they do allow you to import a certificate. That sometimes can be something that a regulator will look for, or an auditor will look for, is for you to use certificates from third parties. You can also export this. So a certificate can be moved between various SQL servers and copied between SQL servers by exporting it and then re-importing it into the other server. And we can use this for a lot of different things. We can use it to encrypt the symmetric keys, like I already mentioned. It's probably one of the most common uses of a certificate in the SQL Server. But we can also use it to encrypt connections and just even secure the connections. We can use it to authenticate a user. We can use it to sign procedures. We can use it to sign assemblies that are going to be imported into SQL Server. There's a number of different ways which certificates are used within SQL Server, and this is only scratching the surface of what exactly they're used for. So let's see how all of this is done. Okay, so we're going to use the same database again. And we're going to start by creating a master key. Within SQL Server, there's a hierarchy of keys. Symmetric keys and asymmetric keys are at the bottom of that hierarchy. At the top of the hierarchy, and you can have any number of layers of those in there, at the top of the hierarchy are the master keys. And each key encrypts the one below it. So we start with the service master key at the top. Then we get to a database master key. We'll talk a little bit more about both of those in a minute. And then below that, you have typically a certificate and then a symmetric key. For the master key, we just provided a simple password, and it handles everything from there using the service master key and Windows API. Okay. And then a good practice, anytime you're creating any sort of a key that can be backed up, do it. Do it immediately. First, back it up somewhere. Because if you lose that key, you lose everything that's associated with it. So we're going to back it up to an external file. Then we're going to create our certificate. There's two fields that are required anytime you create a certificate. One is the subject. That's just a textual description of what it is that this certificate is for. The other is the expiry date. I mentioned that pretty much every certificate out there does have some sort of an expiration date. SQL Server enforces the expiration date on a certificate in some cases, but not in others. Most notably, it does not enforce the expiration date on encrypted data. And the reason for that's simple. They don't want to be responsible for you losing access to all of your data in the case that you go 3 days past the expiration date or 3 years past the expiration date, and you can no longer get at it. So they do not enforce the expiration date for that. However, even though it's not enforced, doesn't mean you shouldn't pay attention to them. So go ahead and create your expiration date or your certificate. Then we're going to create a symmetric key, and we're going to tell it that the encryption in this case is by certificate CER Demo 1, which is the one I just created. You can also specify a passphrase, as I mentioned. In this case, the certificate is the stand-in for the passphrase for the symmetric key, and this is the common pattern. You can have any combination of 2 encryptors on a symmetric key at one time. Okay. If you specify a certificate that SQL Server is able to open automatically, it will. And you don't have to know the passphrase. And that makes it very good for using for data that you're encrypting, where especially if the developers are not supposed to have access to directly decrypt the data themselves. Okay, that's a very common requirement, is that the developers don't have access to decrypt it. So we've created all our keys now. We've got the master key at the top. We've got the certificate in the middle. We've got the symmetric key at the bottom. And now we're going to create a procedure to actually do that. The DBA could create this and just pass it off and say, here, use this procedure. In this, we have the one statement to open the symmetric key. We tell it what certificates that we need to use to decrypt it. And then, oh, by the way, that most of these objects can be controlled by permissions as well. So you could, if there's somebody you don't want to be able to decrypt the data, don't give them access in SQL Server to the certificate, and they won't be able to.
But if they have access to run the procedure, even if they don't have access to the certificate, they should be able to run the procedure.
Yes. And then in order to actually do this, to do the encryption, you use the encrypt by key function. For whatever reason, and I've never seen an explanation for this, but for whatever reason, instead of passing just the name of the symmetric key you want to use, you need to pass in the GUID associated with that. And so there is a key GUID function for that symmetric key, or to be able to allow you to pass in the name to get that GUID. You don't have to go and look it up in a separate table. But that is one thing to know, is that you do have to pass in the GUID, not just the name. Otherwise, the only other thing you have to pass in, and there's a couple of optional parameters, but the only other thing you have to pass in is the value you want to encrypt. In this case, we're going to encrypt a credit card number. And then the symmetric key, because that's just a good way to do nice clean code. So we'll create our procedure. We'll encrypt some data here. And now we can see that we've got our have our account numbers in our table, but they are encrypted, and we've got the last 4 digits in this table just for reference purposes. Ideally, you wouldn't want to necessarily store that in most cases, but we're doing that in this demo. Decryption is equally easy. You open the symmetric key. You do the decryption. You tell the decryption by certificate, just like you did before. To open the key. Select star. We're going to tell it to decrypt by key. We don't have what symmetric key to use. It will look at all of the open ones. And if I pull this back up, one thing you might notice about all of these is that they all start with the same series of hex characters. This is a thumbprint of that symmetric key. This is how it can match up without you having to explicitly tell it which symmetric key is being used. Okay. So it's able to match up the symmetric key and decrypt the data for you without you having to be very explicit. Oops. The one other thing to know, come on, there we go. The other thing to know is that you do need to convert this. You want to convert it back into whatever data type you want. Any encrypted value will be stored in your database as a bar binary. The length of that bar binary depends on the algorithms that's being used. The longer the key value, the longer the resulting encrypted value will be. But it's always started as a bar binary, and so you actually have there are actually a couple
Is that right? Or
certificates in many cases, they don't have to, but they are the hierarchy. The database master key is at the top of that hierarchy with, and then above that, master key.
if they took a backup of your master database and your client?
Guards in there to prevent that sort of a breach. It's not quite that system. However, each piece that they take is one step forward. So,
And that becomes relevant if you're doing, even regardless.
and usable by everything on as well. Our payment info on this. If for some reason you do not successfully value, for security reasons. There's less information. You need to open the key, but you don't, on the decrypt by key statement, you don't have to specify it. It will look at the open ones and see if there's one that's open that it's able to use. See if the right one.
Explicitly open.
It does have to be open, and that's just a security feature. Nothing I know of.
Okay.
Nothing I know. File. And this is important if you need to move the certificate from one machine to another, or if you purchase that certificate from a third party. I'm actually working on a post. I haven't had a lot of time this summer to write it, but I'm working on a blog post that and imported into SQL Server. It's actually gotten a lot easier over the whole process. Pretty simple now. But in general, with once you get into the CER and PDK format, it's pretty easy to import it into SQL Server. You get the first file here, the CER file, is your public key, and then you can specify your private key. You have a PDK extension. And then there's also instructions here on how to keep that this is a simulation. Some of these steps in the middle, don't do on a real server. This is only for the simulation, such as force review. If you have to work right, just can't get it to work right. The master key is out of sync. You can use this force command in order to put the master key right out and get it to encrypt it the right way. Okay. It's a little circumstance. It's not a first resort thing. Talking about the encryption hierarchy. It's a little bit, I don't really like this diagram very well, but it's the best one I found. It does illustrate what I was talking about earlier, where at any one point in time, if you draw a line straight down, you're going to get a combination that you need. The most common one is to use the master key protecting some sort of an asymmetric key or certificate, which protects your symmetric key, which protects your encrypted data. Okay, and at the top, you can see the database master key and the service master key. We already talked about the master key to some extent. The master key can be encrypted by multiple encryptors. So that will allow key rotation if you need to as well. stored it out. Windows always. You always want to use SQL Server Configuration Manager to change the service account of your instance of SQL Server. Because if you don't, the service account will become out of sync with the service master key, and you will no longer be able to decrypt any when to change that service account. Stored on disk. Older versions of SQL Server can't natively read. And if you back and restore something from 3 years ago, unless you have the original page, decrypts it, and puts it into the buffer cache. As long as it's in the buffer cache, it is decrypted. Once it is ready to be where